Hi friends, myself S. Shaktivir from CSM A&ML. My topic is that effective permittivity measurement of 3D printed dielectric crystals. Introduction. Permittivity defines how a material interacts with an electrical field. In 3D printed dielectric crystals, accurate measurement of effective permittivity is crucial for applications in antennas, microwave devices, and metamaterials. What is effective permittivity? Effective permittivity is a concept used in materials science, electromagnetics, and electrical engineering to describe the overall permittivity of a composite or heterogeneous materials. It represents how an electrical field interacts with a mixture of different dielectric materials as if it is were a signal homogeneous medium. Primitivity basics. Primitivity measures how a material resists or allows the formation of an electrical field with it free space. It is denoted as E naught. In materials, it is E is equals to E R1 into E naught, comma, where ER is the relative permittivity, dielectric constant. Effective permittivity. When a material not uniform like a composite mixture or layered structure, the electrical field doesn't interact with all parts equally. Instead, the response depends on effective permittivity. EFF represents the average dielectric constant of a composite or structured material. It depends on material composition, geometry, and air inclusions. Critical for designing photonic and electromagnetic structure. Dielectric crystals and 3D printing. Dielectric crystals are solid materials that do not conduct electricity but can support an electrostatic field. Their main characters Characters are dielectric crystals are periodic materials that control electromagnetic wave propagation. 3D printing enables fabrication of complex geometrics with tunable dielectric properties. Common materials PLA, ABS, resin composites with ceramic fillers. Importance of measuring effective permittivity. Measuring effective permittivity is extremely important in various fields of material science, electronics, and electromagnetic engineering because it determines how materials interact with the electric fields and electromagnetic waves. Here's a detailed explanation. Ensures accurate modeling of electromagnetic performance, validates printed materials quality and uniformity, helps in designing antennas, waveguides, filters, and clocking devices, enables comparisons between simulated and real-world performance. Factors affecting permittivity measurement. We called as measurement permittivity also. Accurately can be tricky because many factors can influence the measurement. Understanding these factors is essential for reliable characterization of materials. Here's a detailed overview. Printing parameters, layer height, infill density, orientation, material heterogeneity and porosity, measurement frequency and temperature, surface roughness and air gaps. Common measurement techniques. Measuring effective permittivity accurately is critical for designing electronic devices, RF circuits, and material research. There are several comic techniques and each is suited for different frequencies, materials types, and accuracy requirements. Here a structure overview. Parallel plate capacitor method. Principle measures capacitance of a sample placed between two conductive plates. Formula EEFF is equal to C into D by E naught into A. C is equal to measured capacitance, D is equal to sample thickness, A is equal to electrode area, E naught is equal to permittivity of free space. Applications low frequency measurement, simple dielectrics. Advantages easy in inexpensive. Limitations not suitable for high frequencies. Edge effects can introduce errors. Conscial probe transmission line method. Principle a coaxial probe is placed in contact with the material. Reflection and transmission or microwave signals are analyzed. Frequency range typical 1 MHz to several GHz. Applications characterizing dielectric liquids, composites, and thin sheets. Advantages not destructive board bond measurement. Limitations requires careful celebration. Surface must be flat for good contact. Resonant cavity method. Principal material is placed inside a constant cavity. Changes is resonant frequency and quality factor. Q induct permittivity and dielectrics. Mm, Laws. Frequency range, microwave and millimeter wave frequencies. Applications: high frequency dielectrics, ceramics and metamaterials. Advantages: very accurate, good for low lossing materials. Limitations: narrow band requires precise mechanics. Mm, so waveguide method, material sample inserted into a waveguide to measure S parameters. Resonance cavity method, shift in resonant frequency, permittivity. Free space, non-conductive, suitable for large or irregular samples. Transmission line method, measurements, propagation delay and attenuation. Resonant cavity technique. A dielectric sample is placed in a cavity resonator. Resonant frequency, if not shift and Q factor change are measured. Effective permittivity is computed using perturbation theory. EFF is equals to 1 plus delta F by delta naught into K, where K depends on cavity geometry and mode. Free space measurement setup uses on antennas and vector network analyzer VNA. Measures reflection and transmission coefficients S11, S21. Suitable for high frequency applications and non-planar samples. Effective permittivity extracted using Nicholson-Rossware NRW method. Experimental setup example: a 3D printed dielectrical cube placed between two horn antennas. VNA records scattering parameters. Celebration with reference air and known materials. Data processed using electromagnetic simulation software. Example: CST HFSS. Data analysis and validation. Compare measured EFF with simulated values. Account for losses and porosity effects. Statistical averaging over multiple samples improves accuracy. Validate using both time domain and frequency domain techniques. Applications of 3D printed dielectrics. 3D printed dielectrics are becoming increasingly important in electronics, photonics, and material science because 3D printing allows complex geometrics, tailored primitivity, and rapid prototyping. Here's a detailed breakdown of their applications. Microwave and millimeter wave antennas, 5G communication components, photonic crystals and metamaterials, biomedical sensors and electromagnetic shielding. Challenges in measurement. Measuring effective permittivity EEFF accurately can be challenging due to several materials, environmental and instrumentation factors. Understanding these challenges is important for reliable characterization. Surface roughness causing scattering losses. Difficulty in controlling infill and air inclusion ratio. Calibrations errors in free space and waveguide setups. Frequency dispersion at high GHz ranges. Recent research trends: use of machine learning from primitivity prediction, multi-material 3D printing for gradient dielectric structures, non-destructive and in situ permittivity measurement methods, integration with AI-based material optimization. This is recent research trends of electric Effective permittivity. Conclusion. Effective permittivity measurement is essential for accurate modeling and optimization of 3D printed dielectric crystals. Combining traditional electromagnetic measurement techniques with modern 3D printing and data-driven analysis enhances precision and enables next generation device development.